Welcome to Learning Management System of Department of Collegiate and Technical Education, Department of Mechanical Engineering, Course Machine Design. Course code is 15ME53T for the 5th semester Mechanical Engineering. Unit 4. In this session, we are going to learn about simple problems on flange coupling. Now, let us read the problem. Design a cast iron flange coupling to transmit 15 kW at 900 RPM from an electric motor to a compressor. The service factor may be assumed as a 1.35. The following permissible stress may be used. Shear stress for the shaft, bolt and key materials equal to 40 megapascal. Crushing stress for bolt and key is equal to 80 megapascal. Shear stress for cast iron is equal to 8 megapascal. Now do the solution now and list out the given data by reading the problem. Now the design a cast iron flange coupling to transmit 15 kilowatt. The power P is equal to 15 kilowatt. And N RPM 900 RPM from an electric motor to a compressor. The service factor may be assumed as 1.35. The following permissible stresses may be used. That is, permissible stresses for the shaft, shear stress for the shaft, bolt and key are the same one. That is because all are made up of same material, that is 40 megapascal. Okay. Now T maximum is equal to T mean into 1.35. You multiply the service factor into the T mean. In the previous we calculated the torque from the power equation. That is T is equal to P 9.55 into 10 to the power of 5 into P divided by N. That is we obtained the torque from the power equation. That is the power equation. Here that what we obtained from that equation is the average torque or the mean torque. Here he has given that service factor 1.35. You multiply that what we obtained from that equation to a service factor, that will get a the maximum torque to be transmitted. Now the next is allowable shear stress or permissible shear stress for the shaft, bolt and the key is 40 Newton per millimeter square, and for the crushing stress for the key is 80 megapascal, that is 80 Newton per millimeter square, and crushing stress for the cast iron is equal to 8 megapascal. Now let us move on to the one by one. For design of the shaft, design of the hub, design of key, design of flange, design of the bolt, okay, etc. Now design of the shaft. Let D is equal to diameter of shaft. Before going to the design the D, here calculate the mean torque. What we obtained from this equation is the average torque or the mean torque. Calculate the mean torque with the help of the power, given power and given RPM. Then use this to calculate the maximum torque. Consider the service factor while transmitting the maximum torque. T maximum is equal to T mean into 1.35, that is service factor. After substituting the T mean here, we have got the T maximum, that is 214.875 Newton millimeter. Now use this to calculate to design the diameter of the shaft. Okay, design of shaft. Use the maximum torque to calculate the diameter of shaft. The maximum torsional shear stress due to the torsional load is given by tau is equal to 16T by pi d cube. Now extract the diameter from the above equation and substitute the values here and calculate the D. D is equal to cube root of 16T divided by tau into pi. Substitute the values of T maximum and tau in the above equation and calculate the diameter of shaft. D is equal to cube root of 16 into 214875 divided by 40 into 5. Now D is equal to 30.13 millimeter. Now after calculating the diameter from the power, that is the torque, and the pure torsion equation, that is the above equation. Now select the standard diameter. Standard diameter means that is the diameter available in the market. For that diameter we have, that is accessories, that is bearings, pulleys, gears, that's why they are given that is the standard diameter that is available in the market. Now go to the data handbook and select the standard diameter from the table. Select the standard diameter of the shaft from the table. Data handbook table 3.5 and page number 57. That is the standard diameter of the shaft is. Now see, go to that here. We have that the standard diameter is available, but we have that is from the equation is available between the 28 and 32. We select that is the larger diameter, that is the 32. Now the standard diameter of the shaft is D is equal to 32 millimeter. Design of hub. The usual proportions of the hub used in the practice are D1 is equal to the hub diameter is equal to D times the diameter of the shaft. That is D1 is equal to 2 into 32 millimeter, that is 64 millimeter, and length of the hub L is equal to 1.5D millimeter, that is 1.5D into 32, then L is equal to 48 millimeter. Now let us now check the individual shear stress in the hub. Torque transmitted by the hub is equal to the pi by 16 into D1 to the power of 4 minus D to the power of 4 divided by D into tau. Here we are going to assume the hub has a hollow shaft. Now this equation is taken from the design data handbook, the equation number 13.3 and page number 252. Now here substitute the values, that is the torque D1 and D here, and calculate the stress, that is induced one. After calculating the tau here, comparing with the allowable one, and conclude whether the design is safe or not. Let us see here now. Substitute the values of the T maximum, D1 and D in the above equation, and calculate the individual shear stress in the for the sleeve. Tau is equal to, now we have the 2.26, that is the individual shear stress in the hub area. Now since the individual shear stress in the hub cast iron is less than the allowable shear stress, tau 8 Newton per millimeter square of the hub, therefore the design of the hub is safe under the given condition. Design of the key. After designing, that is the shaft and hub diameter, you design of the key. The next is step is design of the key. Here the design of the key dimensions are selected from the standard, the table. These are the table. From the table 4.1 page number 69, we find that factor the shaft for the find that for a shaft diameter 32 millimeter, width of the key B is equal to 10 millimeter. Let us see the table here. The table from the data handbook, and here we have 32 here. The for a shaft diameters above 30 and 30 above up to 38. Now we are going to use a dimensions of the key. Width of the key is equal to 10 millimeter and height of the key is equal to 8 millimeter. Now like this we are going to select, that is the dimensions of the key. Now move on to the original stage. Now the width of the key 10 millimeter and height is equal to 8 millimeter. Since here the crushing stress for the key material is twice the shearing stress, therefore a square key may be used. Sigma c is equal to 2 into tau. Tau is equal to 40 Newton per millimeter square, allowable shear stress for the shaft and the key. Then sigma c is equal to 18 Newton per millimeter square, allowable crushing stress for the key material. Therefore height of the key h is equal to 10. Once that is the crushing stress is twice the shear stress, we are going to use that is square key. That is height and width are the is equal to the same. We know that the length of the key is equal to length of the hub. L is equal to length of the hub is equal to 1.5 into d millimeter. That is equal to 48 millimeter. After selecting the dimensions of the key from the table and calculating the length of the key with the empirical relations, you check the induced shear stress and crushing stress in the key meter here. Okay. Now let us check the induced shear and crushing stress in the key. First of all, let us consider the shearing of the key. Shearing strength. T is equal to half into tau into B into dl. Extract the tau from here, the induced shear stress. Substitute the values of T, B, D and dl. Then T is equal to 27.97. It is induced shear stress. Similarly, now check the crushing strength of the key here. The T is equal to half into sigma B into H into D into L. Then sigma B is equal to T into 4 divided by H into D into L. Sigma B is equal to 55.95 Newton per millimeter square. Now comparing these individual shear stress and crushing stress with that of the allowable one. Individual means while transmitting these are the stresses are developed in or created in the elements of the key. That is, once this induced shearing and crushing stresses are less than the allowable one, then the design is safe under the given condition. You write the conclusion after calculating this here. Then since the individual shear and crushing stress are less than the allowable stress in the key, therefore the design of the key is safe under the given condition. Now let's move on to the flange here, design of the flange. Now we have that is empirical relations. Usual proportion of flange usually in practice are D1 is equal to the hub diameter, that is equal to 2 times the D. We are taken this one from the data handbook, that is equation number 13.1 D and page number 252. D1 is equal to 2 into 32, that is 64 millimeter, that is the hub diameter. And D2 is equal to diameter of the board circle, that is equation number 13.1 E and page number 252. And D2 is equal to 3D, D2 is equal to 3 into 32 into 96, that is the D2 is equal to 96 millimeter. And D3 is the outer diameter of the flange, that is D3 is equal to 4D and D3 is equal to 128, that is 4 into 32. Now T is equal to thickness of the flange. Now here is the empirical relation, T is equal to 0.35 D plus 9 millimeter. Now we have the 20.2 millimeter. I will round up to the next even number, that is the 22. Now here the dimensions of the flange, that is thickness of the flange, outer diameter of the flange and the diameter of the board circles, all are obtained from the empirical rule. Now after fixing that dimensions of the flange with empirical rules, now check the induced shear stress in the thickness of the flange. Now the flange may failure in between the hub and the flange junction. It may failure in the form of the shearing. Okay. Now let us check that is the individual shear stress in the flange now. Now torque capacity based on the shear of the flange is given by D1 is equal to 64 the hub diameter and D2 is equal to 96 the diameter of the board circle and D3 is equal to 128 millimeter. Now T is equal to 22 the flange thickness. Now let us see where actually the failure will be that takes place. Now for example, this is the flange, this is the hub, this is the hub, and this one is the flange. Okay, now this is the shaft. We have the key, that is shaft. It may failure at this junction, Okay. Now here the dimensions of that is hub diameter is D 64 millimeter, D2 is 96 millimeter, and this is 120 millimeter. That is D3 is outer diameter of the flange. This is the D3, and D2 is the board circle diameter. Here we are going to put the boards here. This is the what D2 here, and this is the up diameter D1 here. It may fail at this junction. Now this is the thickness of the flange here, T. Now before that is area resisting that shear is given, the area into the force that gives the torque transmitting capacity. Now we are see from the formula, the torque transmitting capacity of this flange is equal to this one, T is equal to tau into pi into d1 square into T divided by 2. Now you extract the tau from here and substitute the values and calculate the individual shear stress. Now after substituting the values of, that is the dimensions of the hub here, the torque transmitting and D1 and T here, calculate the shear stress in the cast iron flange. Now we compare this one to the allowable shear stress. Since the individual shear stress is less than the permissible shear stress in the flange, therefore the design of the flange is safe under the given condition. Now design of the bolt. Calculate the number of bolts required to the coupling with the empirical rule. Now I is equal to number of bolts is given by I is equal to 0.02D plus 3, that is 0.02 into 32 plus 3, that gives the 3.64 approximately 4 number of bolts. D2 is equal to 96 millimeter, the diameter of the bolt circle, and T is equal to 22, that is the flange thickness. Now the diameter of the bolt may be determined by the empirical formula. D is equal to 0.423 D divided by I plus 7.5 millimeter. Substitute the values of D here and calculate the D. That is D is the nominal diameter of the bolt. You select the standard diameter from the table here. The table 9.8. This is the page number. It is table number 9.8 from the threaded fastener. Now we have the 14 and the 16. The nominal diameter is only 14 and 16 here. The next diameter after the 14 is 16 only. Therefore, select the diameter of nominal diameter of the bolt is 16. Now check the shear of bolt by considering the equation. Determine the diameter of the bolt by considering the torque capacity based on the shear of bolt. And here we are going to check the individual shear stress in the bolt material. That is shear stress, individual shear stress in the bolt material is the 5.56, and since the individual shear stress is less than the permissible shear stress in the bolt, therefore design of the bolt is safe under the given condition. Now thank you. That's all. That is the design of the flange coupling. I have taken some instructions, some information from the textbooks of machine design by the R.S. Kurmi and Siglesh Mechanical Engineering design by the Richard and G. Budjans and J. Ketan Nesbet, design of machine elements by the J.B.K. Das and P.L. Srinivas Murthy, design data handbook by the K. Mahadevan and Dr. K. Vallabhareddy, and fundamentals of drawing by the K. R. Gopal Krishna. And once again I thank you. Thanks for our teammates, the moderator and subject experts and my colleagues for the development of this one.